All right, Chapter 11, Section 3, Areas of Polygons. For the record, up until this point, we have, in several math classes before this one, talked about areas of various polygons, ones that you will be familiar with. In Section 2, for the record, a circle is not a polygon. Or you can make an argument that it is a one-sided figure. It's just the one curve. But the area of a circle being pi times r squared, that was the focus of Section 2. But as far as other polygons, to use the term properly, things like a triangle, the simplest polygon, we have dealt with the area of a triangle. We did a little bit in Section 2 for the dartboard problem. The area of a triangle is 1/2 base times height, as many of you will know from previous math classes. And you will be definitely familiar with the area of some of the simpler quadrilaterals or four-sided figures, namely a square or a rectangle, length times width. For a square, it happens to be the same measurement. And then it gets a little more complicated for different kinds of quadrilaterals, like a trapezoid or something like that. It's still technically length times width. It's just that if you have varying lengths to sides, like in a trapezoid, you're taking an average length or average width. And that kind of dictates the formula. But quadrilaterals, typically, it just breaks down to length times width. In this first clip, we're going to talk about two very unique quadrilaterals that you see here on the board right now, a rhombus and a kite. These are actually terms that we've dealt with previously in the year, earlier in the semester. We introduced the rhombus and kite in our quadrilaterals talk and our unit on parallelograms and that sort of thing. The formula here for solving for the area is essentially, again, kind of a length times width. There's a 1/2 involved. It has to do with the fact that we're not dealing a pure length and width. We're dealing with diagonals here, which is actually an easier measurement with both the rhombus and the kite. I'll talk about those in a second. But the main meat of this section is actually going to be in clips 2 and 3 as we move forward in here, where we get into other polygons. Typically, for geometry units, for high school students in particular, you focus on like the simpler polygons, the 3-sided figures, the 4-sided figures. We're going to start exploring areas of polygons that we have never come across before, or at least in form of finding the area of those polygons. So you're going to see some new formulas here in this section. But before we get into that, let's just get our feet wet with a simple formula for the area of simple 4-sided figures, being a rhombus and a kite. So just pointing out these definitions one more time. This is something that you have come across before, but a rhombus by definition is just any figure that has 4 congruent sides. So for the record, a square is a type of rhombus because it has 4 congruent sides. It's just that a square is the specific rhombus that also happens to have 4 right angles. Another way that you'll hear this one called, you've probably identified it this way before as well, it's also called a diamond, okay? But 4 congruent sides, looks like a squished square. And then a kite is really the same shape fundamentally. It's just that it's like you took this little diagonal right here and you moved it to one side or the other. So in this case, it just kind of moved a little bit to the left. We're all kind of familiar with kites as they are because the actual kite itself, the flyable kite, takes on this shape for that reason. But in these cases, the formula kind of breaks down simply like this. How to find the area of these shapes. I'm going to take each diagonal length. Each diagonal length, the diagonals being what the distance would be across, both long ways and width wise, in each of these shapes, whatever they may be. I'm going to multiply those 2 diagonals together, and then I'm going to cut that in half. That's the area of a rhombus and a kite. Again, both are essentially the same shape from an area standpoint, finding this 2-dimensional measurement of square units on the interior. Again, just take each diagonal, multiply it together, and then cut that result in half. Students tend to forget this 1/2, so just make sure you're not one of those students. A couple quick examples of applications. You will come across a couple of these in your first few problems and big ideas. This would be a rhombus right here, part A, simply shown by the 4 congruent sides, also described as a diamond. We're explicitly told real numbers here, 6 meters across wide ways, 8 meters tall. These would represent the diagonal lengths. So I'd simply multiply those values together. 6 times 8 would give me 48 square meters. Just remember that I'm cutting that value in half. So 48 square meters cut in half is 24 square meters That's the area of this rhombus. Part B, this would be a kite, as shown by the two different pairs of congruent sides, right, and the general kite shape. And again, they kind of explicitly show us the lengths of each of the diagonals, 10 centimeters long, 7 centimeters tall. In some cases, they'll actually show you on the inside, where like these dotted lines are, they'll actually show you the length of those. But again, I'll just multiply each of those diagonal lengths together. 10 centimeters times 7 centimeters gives me 70 square centimeters. Just remember to cut that in half. So that'd be 35 square centimeters for the area of that kite. Quick variations that you might come across. In both these examples, you were shown actual real numbers for the lengths of those diagonals. They could give you algebraic phrases, like they could say like this is x units long, and this one's x plus 2 units long. And then they would tell you in that case the area of this figure would be so many square units. And so you just plug those values into this formula. In that case, you would be solving for a variable. Okay, that's about as complicated as it gets, though. In that case, you're just, again, distributing, solving for a variable, using the inverse operations to get to the other side. But this would be the formula for the area of either a rhombus or a kite. And they'll be pretty distinguishable when you come across them because they'll look like these guys. But that will conclude our first clip here on areas of polygons. This is just getting our feet wet with a couple of simple quadrilaterals, which are polygons. They're four-sided figures. But what we're going to start exploring in the next couple clips is what happens if we aren't dealing with these simpler polygons, namely three-sided triangles or four-sided quadrilaterals, which we've been kind of familiarized with in a few different units this Math 2 year. But what happens when we start dealing with more sides, pentagons, heptagons, decagons, dodecagons? What happens with the area of those shapes? But that will be in our next couple clips. I'll go ahead and stop this clip right here.